What specific problem does the new method aim to solve in the context of establishing shared intentionality between agents?
The new method aims to solve the problem of enabling agents to establish shared intentionality without relying on predefined external rewards or explicit communication protocols. By utilizing intrinsic motivation functions, the method encourages agents to prefer self-other interactions based on mutual information and the desire to influence and be influenced by each other. This approach addresses the limitations of previous evolutionary robotics simulations, which required an oracle to determine interactions, thus failing to generalize to other tasks. The method specifically investigates how agents can develop turn-taking and imitation behaviors autonomously, fostering primary intersubjectivity and enhancing their ability to create shared understanding. Ultimately, it seeks to demonstrate that agents can achieve effective social coordination and communication through intrinsic drives, even in the absence of extrinsic rewards.
Can you explain how the proposed method works? Illustrate the methodology step by step, including how the agents interact in the perceptual crossing paradigm and the roles of the reward functions.
The proposed method utilizes a multi-agent interaction scenario within a perceptual crossing paradigm, PCP, where two agents occupy positions on a circular line and attempt to elicit crossing events by moving left, right, or remaining still. Each agent receives feedback based on their interactions, specifically a buzz when they cross another agent or a stationary object. The agents are trained using a reinforcement learning framework, where they maintain long short-term memory LSTM networks to predict crossing events and their associated confidence levels. The reward functions are designed to encourage specific behaviors. The drive for understanding rewards agents for making accurate predictions about crossings, while the drive for being understood promotes reciprocal imitation and mutual influence between agents. This dual reward structure fosters a dynamic interaction where agents learn to anticipate each other's actions, enhancing their ability to cooperate and achieve shared goals, even in the absence of extrinsic rewards.
Could you provide a simple illustrative example of how the agents interact in the perceptual crossing scenario, detailing the steps they take and how the rewards are structured?
In the perceptual crossing scenario, two agents occupy positions on a circular line and attempt to interact by moving left, right, or remaining still. For instance, if Agent 0 moves towards Agent 1 and they cross paths, both agents receive a buzz, which serves as a reward for the interaction. The reward structure is designed to encourage agents to predict crossings. If an agent's prediction about crossing is accurate, it receives a reward proportional to its confidence in that prediction. Conversely, if the prediction is incorrect, the agent receives an exponentially increasing reward based on the level of certainty it had about the crossing. This setup promotes a preference for self-other interactions, as agents learn to anticipate each other's movements, thereby maximizing mutual information and enhancing their cooperative behavior.
What are the key theoretical and practical advantages of utilizing intrinsic motivation in this method compared to traditional reinforcement learning approaches?
The key theoretical advantage of utilizing intrinsic motivation in this method, as outlined in the paper, is that it fosters a preference for self-other interactions without requiring an external oracle to determine when agents are interacting. This intrinsic drive allows agents to engage in mutual influence and impressionability, promoting a more natural form of communication and understanding that aligns with human social dynamics. Practically, this approach enhances the agent's ability to learn and adapt in complex environments, as evidenced by their improved performance in tasks requiring cooperation, even when only one agent receives extrinsic rewards. Unlike traditional reinforcement learning, which often relies on predefined tasks and rewards, this method encourages agents to explore and create new interaction patterns autonomously, leading to richer and more flexible behaviors. Ultimately, the incorporation of intrinsic motivation results in agents that can better anticipate and respond to each other's actions, thereby improving their overall effectiveness in collaborative scenarios.
How was the proposed method validated in the experiments? Describe the experimental design, data collection, and performance metrics used to demonstrate effectiveness.
The proposed method was validated through a multi-agent interaction scenario, using a 1D perceptual crossing environment, where two agents attempted to elicit and anticipate crossing events by moving along a circular line. Data collection involved tracking each agent's position, actions, and crossing events over multiple episodes, with agents receiving rewards based on their interactions and predictions of crossings. The performance metrics included the mean and standard deviation of returns and crossing proportions, which were averaged over 5 independent runs to assess the agent's preferences for self-other interactions. Additionally, the effectiveness of intrinsic motivation functions, such as the drive for understanding and the drive for being understood, was evaluated by comparing the agent's behaviors under different reward settings, including scenarios with and without extrinsic rewards. The results demonstrated that agents with intrinsic motivations showed a preference for interacting with each other, which was crucial for achieving cooperative behavior in tasks requiring coordination.
What significant results were achieved through the proposed approach, particularly in relation to the interaction preferences of agents and the influence of intrinsic motivation on their behaviors?
The proposed approach demonstrated that agents exhibit a strong preference for self-other interactions, particularly when intrinsic motivations for understanding and influence are incorporated into their behavior. Specifically, agents trained with a drive for understanding showed limited preference for interaction, while those with a drive for imitation and influence displayed a significant increase in self-other crossings, indicating a more dynamic interaction pattern. The results revealed that even when the drive to be impressionable was removed, agents still maintained a high level of self-other interactions, suggesting that the drive to influence alone was sufficient for cooperative behavior. Furthermore, when intrinsic motivations were coupled with an extrinsic reward task, the agent receiving the extrinsic reward, Agent 0, was able to effectively guide the other agent, Agent 1, to the desired region, highlighting the importance of intrinsic motivation in facilitating cooperation. Overall, the findings underscore that intrinsic motivations not only enhance interaction preferences, but also play a crucial role in achieving cooperative outcomes in tasks requiring coordination.